Hello dear students, good morning. Welcome back to the chemistry class. In the last class, we have discussed some of the numericals on the first colligative property, that is a relative lowering in vapor pressure, right? So in this session, we are going to discuss the second concept, the second colligative property, that is about elevation in boiling point. So in this concept, so before going to discuss about the elevation in boiling point, let us recall the definition of boiling point. What is the definition of boiling point? Can you define boiling point? Yes, simple definitions we know that boiling point can be defined as it is the temperature at which the liquid state is converted into vapors, that is gaseous phase, liquids to gas. The temperature at which liquids are converted into gases is known as boiling point. What is the actual definition? In states of matter, we have distinguished between, or what is the actual definition of boiling point? So, the boiling point, it can be defined as boiling point definition. First, boiling point definition. So, here, the temperature at which the vapor pressure of solutions which becomes equals to atmospheric pressure. So this is known as boiling point. The temperature at which the vapor pressure of the solutions when it becomes equals to atmospheric pressure, or the temperature at which the vapor pressure and atmospheric pressure becomes equal, that temperature is known as boiling point, right? Boiling point. So what is the meaning of this elevation? That is nothing but difference. The difference between boiling point of a solution and solvent. So as we have already studied in the first colligative property, that is the relative lowering in vapor pressure. So here, vapor pressure of pure solvent and solution, it is different. The vapor pressure of pure solvent and solutions is different. As you know that already. Why the vapor pressure of solutions is different from the solvent? Because a solutions which containing non-volatile solute, so some of the surface molecules are occupied by solute particles, so escaping tendency of the liquid decreases, vapor pressure decreases. So here same thing. So here first, in a beaker I have taken pure solvent. So let us assume that this is a pure solvent in a closed vessel in the first case. So this is the surface molecules remaining is solvent. So in pure solvent, whatever the pressure exerted, this is called as vapor pressure of pure solvent A. A is a solvent. Now in the second beaker, I have added little solute. So when little solute is added, it becomes solution. This becomes solution. So now here, in the surface molecules, in relative lowering vapor pressure, already we have studied. When solute is added, some of the surface molecules, solute particles occupies some of the surface. So as a result, escaping tendency of the liquid becomes less. So vapor pressure decreases. So here vapor pressure of solvent is greater than vapor pressure of solution. Now elevation in boiling point. So this can be expressed graphically. Let us see the explanation of elevation in boiling point graphically. So here in one axis we are taking the vapor pressure. On x-axis, let us take this as a temperature versus vapor pressure. Assume that this is the atmospheric pressure, constant atmospheric pressure. This is atmospheric pressure. Now I have taken two components. One is solvent. Let us call as A is a solvent, and the second one is solution, that is B. One is a solvent and one more is solution. Now vapor pressure among these two beakers, in which case the vapor pressure will be more? 100% in solvent. In case of solvent, the vapor pressure will be more than solution. So let us represent these two by putting a point. This is vapor pressure of two different, one is solution and one more is solvent. So here vapor pressure, this point let us call as B and this is A, because A is a solvent having higher vapor pressure than solution, therefore I have represented A and B. This is at a particular temperature, I have considered. Now when both the beakers, when both solvent and solutions are heated, I am increasing the temperature. What happens when temperature is increased? The vapor pressure gradually increases. This also increases, and at a particular temperature it reaches the atmospheric pressure. So the temperature corresponds to this point is called as boiling point, TB, and this is for solvent, so therefore I am representing naught, T naught B. Boiling temperature of solvent. Now when solution is heated, the its vapor pressure is less, so it also gradually increases, and at a particular temperature it reaches the atmospheric pressure, and that temperature is known as boiling point of solution. TB, T naught B. So TB, this represents boiling point, boiling temperature of solution, boiling temperature of solvent, solution and solvent. This difference between the temperatures is known as delta TB. Delta, that means change. The difference between TB and T naught B is known as elevation in boiling point. This difference is called as elevation in boiling point. So how to define this delta TB? It can be defined as the elevation in boiling point is defined as, in this case you can note this, TB, delta TB is equals to higher value is for solution. So TB minus T naught B. Please note this, delta TB is equals to TB minus T naught B. TB minus T naught B. So here define this. So it is the difference between elevation in boiling point can be defined as, it is the difference between boiling temperature of solution and boiling temperature of solvent is known as elevation in boiling point. So now mathematically I have given. Now experimentally we know that, so this delta TB values, delta TB is directly proportional to molality, small m, directly proportional to molality. So experimentally we know that it is shown that experimentally, so we have delta TB is directly proportional to small m, that is molality. So if you remove this proportionality, the proportionality constant delta TB is equals to Kb into m, where this Kb is known as ebullioscopic constant. Ebullioscopic constant, or it is also known as molar or boiling point constant. Molar boiling point constant. Molar boiling point constant, and its unit is abelioscopic constant. Its unit is important. Its unit is Kelvin kg per mole. Kelvin kg per mole. Or simply we can write Kelvin per mole degree Celsius kg per mole. Delta temperature degree Celsius, or simply we can write Kelvin kg per mole in SI, or degree Celsius or Kelvin we can use per mole. So this is the unit, and its definition is, how we are going to define this? So kb is nothing but, what is the definition? See that definitions here only it is there. So if m value is equals to 1, what happens? When m is equals to 1, kb becomes equals to delta tb. So you can define abelioscopic constant or molar elevation constant. It can be defined as, it is the difference between, kb is the difference between boiling temperature of solution and solvent for 1 molar solution. Definition in Bhartili, when m is equals to 1, that is for 1 molar solution, kb is defined as delta tb. This is the definition. So for 1 molar solution, whatever the temperature difference is there, that is equals to kb. So where kb is molar elevation in boiling point, molar boiling point constant, or simply we can call it abelioscopic constant. Its unit is Kelvin kg per mole. Its definition is, it is the difference between the temperatures of, difference between the boiling points of solution and solvent for 1 molar solution, compulsory for 1 molar solution. So this is the concept, elevation in boiling point. Is it clear? See here, second colligative property, that is elevation in boiling point. The first point, you know the definition of boiling point, that is the temperature at which the vapor pressure become equals to atmospheric pressure is called as boiling point. So elevation is nothing but there is difference, one is a solvent and second one is solution. So for solvent, vapor pressure is more, so therefore very less temperature is required to reach the atmospheric pressure, hence the boiling temperature of solvent will be less. When some amount of solute is added, the vapor pressure is decreased. So it takes more temperature or more heat energy to reach its vapor pressure to atmospheric pressure, and hence the boiling temperature of solutions is always greater than solvent. This difference between the boiling temperatures of solvent and solution is called as elevation in boiling point. And this elevation in boiling point, experimentally it is given as, or it is depends on molality, not molarity, not capital M, it is a small m. So here, where this is the proportionality symbol, so delta Tb is equals to Kb into m, where this Kb is proportionality constant called as abelioscopic constant and its unit is Kelvin kg per mole, and its definition is for 1 molar solution, Kb is equals to delta Tb. This is the definition of molar elevation in boiling point, that is elevation in boiling point, right? Now the main point, simple, determination of molar mass. In for colligative property we need to calculate molar mass, that is the main point. So determination of molar mass by using this colligative property. How to determine the molar mass from elevation in boiling point? Very simple. So in place of m, write its definition or substitute the formula of molality and rearrange the equation. You will get the equation for, or the formula for molar mass of solute. Molar mass of solute. So let us determine the molar mass of solute from colligative property. So as we know that delta TB is equals to KB into M, where M is molality. What is the formula of molality? Molality is equals to number of moles of solute present in 1 kg of solvent, WA into 1000, right? So NB is nothing but what? Given mass of solute divided by molar mass of solute whole divided by weight of solvent into 1000. So this is the formula of molality. In the beginning we have studied. So now just substitute this formula in the equation. We'll get delta TB is equals to KB into molality, KB into WB into 1000 divided by MB into WA. Now we want the formula for molar mass. So therefore molar mass of solute is equals to KB into WB into 1000 divided by delta TB into WA. Please note this formula. This is the second formula, second main formula. The first formula is from relative lowering in vapor pressure we have calculated molar mass, and this is the second formula. We have calculated the molar mass from elevation in boiling point. So elevation in boiling point, where you can represent MB is nothing but it is the molar mass of solute. It is the molar mass of solute. Second one, WB, given mass of solute. Given mass of solute. WA is the weight of solvent. Weight of solvent. KB is its value will be preferably it is given. It is molar elevation constant, or simply we can write ebullioscopic constant. Its value will be given. And remaining the 1, 2, 3, 4. Yes, 1, 2, 3, 4. And one more term, that is delta TB, elevation in boiling point. Delta TB is nothing but the difference between boiling temperature of solution and solvent will be given. So if it is not given, you can calculate. One terms will be given. This in case of water, T0B is constant. Boiling temperature of water is constant. So by knowing that, we can find out delta TB and then substitute and simplify to find the molar mass of solute. So this is the formula to calculate the molar mass of solute from second colligative property, that is elevation in boiling point. Remember one more formula. If KB is not given, so to find the KB value, if it is not given, then it is calculated from the formula MTR, not the sambar masala, MTR. So here boiling point, so TB square, TB square R divided by delta H into 1000, that is enthalpy of vaporization. If latent heat or enthalpy of vaporization is given, then you can find out the KB value and then you need to substitute in the formula to find the molar mass of solute. Molar mass of solute. Now, how these two are related? What is the relation between TB and delta TB? What is the relation? So here TB is equals to delta TB plus T0B. So as the difference value increases, that is elevation in boiling point increases, the boiling point of solutions is also increases. So in this case, please note one more formula, one more short relation for objective. Delta TB is directly proportional to TB. So boiling temperature of solution increases, elevation in the boiling point also increases, that is colligative property increases. So when this increases, molality increases because delta TB is directly proportional to M. So therefore, the boiling point is directly proportional to molality, that is concentration of solute. As the concentration of solute increases, so more amount of solute we are adding to the solvent, so vapor pressure will be decreases. As the vapor pressure decreases, definitely the boiling point increases. So for short objectives, so please note this one more relations, short relations, so for solving the problems, applications level problems. So this is about the second colligative property. So in the next class, we will discuss some of the numericals on the elevation in boiling point. Okay. In the next class, we will solve the problems. Thank you.